Hello everybody, this is Dr. Christopher White and welcome to part 2 of the Precambrian Earth and its life history, focusing on the Proterozoic Eon. Okay, let's get going. So if you remember, one of the changes that we can see in the rock record as we transition from the Archean into the Proterozoic is the appearance of rocks related to glacial processes. So if you remember all the way back to the sedimentary rock lectures, you might remember that there is a very specific type of sediment which is deposited by a glacier, and that sediment is called a glacial till. And all a glacial till is it's simply the build-up of sediment as the ice at the nose of the glacier melts. So if you remember, glaciers will transport a whole range of sediments ranging from clays all the way up to huge boulders, and all of that material is transported within the ice. So of course when the ice melts, all that sediment is liberated and it is deposited, and so this sediment will pile up at the nose of the glacier and it will form our glacial till deposit. Now if we take that glacial till deposit and we lithify it, so we turn it into a rock, we get a type of rock which we call a tillite. So tillites, or visually similar deposits, have been identified from at least 300 Precambrian locations. Now the exact number of locations where we have these Precambrian tillites is a little difficult to know, as some of them have been quite badly metamorphosed and deformed, so they may not be tillites. We're not 100% certain, but there is definite evidence to show that we had glaciations in the Proterozoic. So with regard to North America, we know there are Proterozoic tillites of the same age in Michigan, Wyoming and Quebec in Canada. Now this would suggest that there may have been an ice sheet centred on the southwestern region of the Hudson Bay. We also see tillites of a similar age occurring in Australia and South Africa. However, the dating is not precise enough to determine whether they're part of a widespread glacial event or whether they're just localized occurrences, because one of the problems we have with tillites especially is they are very, very difficult to date accurately, and that's made even more complicated by the fact that these are Precambrian tillites, and therefore we don't have layers of rock above or below them that could contain fossils which would help us work out their approximate age. So if we look at the pictures here, we can see this is an example of a modern till deposit. You can see very mud rich, lots of clasts ranging in size from small ones all the way up to quite large boulder sized clasts. And this is the result of the lithification of this type of sediment. So this is a tillite, and you can see once again we have a very fine grained mud rich matrix which is enclosing quite large clasts. So one tillite, which is from the Bruce Formation in Ontario, has a date of 2.7 billion years. That actually makes it Neo-Archean, so very late Archean. So not all of these early tillites are actually Proterozoic. We do have a few instances where they appear in very, very late Archean rocks, but the vast majority of Precambrian tillites are of Proterozoic age. So tillites and other glacial features are found in Proterozoic strata from between 900 and 600 million years ago. So that's the Neoproterozoics, that's towards the end of the Proterozoic. And we find them on all continents with the exception of Antarctica. And of course it's quite difficult when it comes to Antarctica, because most of the rocks on that continent are of course covered in a big thick layer of ice, so we can't get to them. So glaciation was not continuous during this period, and we think there may have actually been 4 major glacial episodes which we can identify. Now it's important to note that these geologic events all occurred at approximately the same time, and their geographical extent is unknown. So one of the issues we have is we have these glacial deposits that would appear to be around the same age, and so the natural assumption is to go, they must have all been formed by one very large glacial event. Well, as I've just discussed, the problem is that it's very difficult to date these sediments accurately, and so saying they are all formed by the same event is a rather precarious statement. So all we can say is that we have glacial events that are occurring at approximately the same time, but we don't know whether they were linked up or whether these represent local isolated events. However, it would seem that this 300 million year window between 900 and 600 million years ago had the most extensive glaciations seen in Earth history, with some of them possibly extending all the way to near equatorial areas. So you would have had an ice sheet that extended all the way from the poles to just about the equator. So based on the distribution of Paleoproterozoic, so late Proterozoic glacial sediments in North America, we can see that they occur in a region focused on Hudson Bay, and we find especially large amounts of them in the southwestern region, well, the south and southwest of the Hudson Bay area. Now, if we look at a global scale, we are still looking at Paleoproterozoic till deposits, or tillites, and the green areas are the regions where they are occurring. So you can see that there are some very, very large areas where we do have extensive quantities of these Paleoproterozoic tillites. But you're looking at this map and you're thinking to yourself, well, hold on a minute, okay, there's quite a few of them there, but, you know, that's not really particularly great coverage. I mean, look at Asia, for instance, you know, it's practically Proterozoic tillite free. The thing you have to remember, though, is that the map doesn't look that impressive because large parts of Asia, Africa, Europe and South America didn't actually exist in the Proterozoic. So, for instance, you know, we had the Amazonia craton here, we have the Rio de la Plata craton down here, but this entire southern portion of South America, for instance, wouldn't have actually been around during the Proterozoic. Same goes for huge quantities of Asia. Europe didn't even exist. Europe doesn't really begin to make an appearance in a big way until all the way into the Mesozoic. So there are actually large parts of the globe that just weren't around in the Proterozoic, and so obviously if they weren't around, you can't deposit glacial sediments on top of them. So all of a sudden, the distribution that you can see here actually begins to look a lot better when you consider that large quantities of Asia didn't exist, most of Europe didn't exist, and large parts of South America and Africa didn't exist. And so when you look at what's left, well, then all of a sudden you think, well, actually, that's pretty good coverage of Proterozoic, well, that's actually pretty good coverage of Proterozoic glacial tills. So as late Proterozoic glacial deposits and structures are so widespread, it's led to a theory that there was at least one massive glaciation event towards the end of the Neoproterozoic. Once again, Neoproterozoic is the late Proterozoic. And this event is termed snowball Earth. Now, it's a controversial model as the supporting evidence is so widely spread and in some cases poorly dated or deformed or metamorphosed, so you obviously have to be careful when you are not working with nice pristine rock. So what's the model for this snowball Earth theory? Well, it just so happens that the timing of snowball Earth is believed to coincide with the formation of the supercontinent Rodinia. Now, one of the things you'll notice about the distribution of the continents for this supercontinent is that they are primarily located north and south of the equator. So they're within this equatorial band. Now, this is important because we know from the modern world that rocks which are, or areas of continent which are located along this equatorial band typically suffer very, very accelerated weathering. So there's large amounts of rain and also temperatures tend to be quite warm, and this means that rocks will be weathered very, very efficiently in these kinds of environments. So one of the things that can happen as part of this weathering process is calcium minerals in the rock can actually react with carbon dioxide from the atmosphere to form calcium carbonate. And so this weathering process in general doesn't really make too much difference if you have the continents in their current positions. However, if you were to put a large amount of the continental landmass along the equator where you have this accelerated weathering profile, well, then all of a sudden you have lots of rock being weathered. That means lots of calcium minerals being weathered, and some of those calcium minerals are going to be reacting with the atmosphere to remove carbon dioxide from the atmosphere. And so what you're going to see is you're going to see a steady decrease in the amount of carbon dioxide. Now, at the same time, we are also dealing with period of Earth history where we have lots and lots of photosynthesizing single-celled organisms, and they too are going to be scrubbing carbon dioxide from the atmosphere and replacing it with oxygen. So during this time period, we have a steady decrease in the amount of global carbon dioxide. Now, we also know, that, of course, that carbon dioxide is a greenhouse gas. So, as the amount of carbon dioxide decreases, the greenhouse effect becomes weaker, and so that means the Earth is less able to retain heat. And so global temperatures will begin to decrease. Now, it's possible that the glaciation began at both poles, or maybe it started on a landmass outside these polar regions. I mean, if you look at the predicted distribution, you'll notice that both the poles are essentially free of continental crust. This is actually not the best situation. If you want to form an ice sheet, forming it on continental crust is actually the easiest thing to do. Forming an ice sheet on open water is actually rather complicated. So this means that, there is the possibility the ice sheet started at one or both poles, but there's also the possibility that maybe the ice sheet actually started on one of the more southerly or northerly continental landmasses, maybe something like Siberia or West Africa here, and then it grew out over the rest of the continents. We aren't 100% sure about where the ice sheet started. So as this ice sheet expands, it's actually going to bring increase the global bond albedo. That's essentially a measure of how light the surface of the Earth is. So what we're doing is we're covering the surface of the Earth with ice, which is quite light in colour. We are covering over the dark oceans and the dark continents. So this means that more solar radiation is going to be reflected back into space because the surface of the Earth is going to be lighter in colour. This once again is also going to drive down global temperatures. So this combination of an increasing bond albedo, because the surface of the Earth is getting lighter as it gets covered with more ice, and decreasing carbon dioxide levels, which leads to a decreased greenhouse effect, is going to cause global temperatures to decrease quite rapidly, and it's going to eventually lead to what's referred to as a runaway glaciation. So it gets to the point where the Earth gets so cold that we start forming large quantities of glacial ice. This this increases the bond albedo. That therefore causes the global temperatures to drop even further, which means we get more ice forming, which increases the bond albedo further, and so on and so on and so on. You can see we have this feedback mechanism. As the temperature gets lower, more ice forms, that increases the bond albedo, and that helps to drive down the temperature even further. So all of a sudden, forming a very, very large ice sheet becomes a relatively straightforward process. So what's going to happen once we establish our ice sheet? Well, the first thing to remember is that our ice sheet is going to cover over large quantities of continental crust and a substantial amount of the ocean surface. Now, this is going to affect the amount of carbon dioxide in the atmosphere for two reasons. The first reason is that the ocean is actually quite a large reservoir for carbon dioxide. So normally, carbon dioxide would dissolve from the atmosphere into the oceans. However, the problem is, of course, as soon as you put a big thick layer of ice between the atmosphere and the oceans, this process obviously won't function anymore. So we instantly lose the capacity of the oceans to strip out large quantities of carbon dioxide from the atmosphere. Another problem we have is that by increasing the amount of sea ice, we're obviously reducing the available environments in which life can exist. So you have to remember at this point, life is single-celled and it's going to be primarily marine. So it's going to be living in the oceans. So by covering the ocean surface with sea ice, first thing, obviously that reduces the amount of space in which life can live. But also at the same time, we are decreasing the ocean temperature. This is going to reduce the efficiency of those photosynthesizing organisms. And so that in turn is going to mean that these photosynthesizing organisms will be taking out less carbon dioxide from the atmosphere as part of the photosynthesizing process. So we are going to see a steady increase in atmospheric CO2 because it's not being removed. So the next question is, of course, where's that CO2 coming from? Well, most of the CO2 is going to be coming from volcanoes. So the volcanoes during this period, they're going to keep erupting. They're going to release carbon dioxide as part of the gaseous portion of the eruption. Within that, along with that carbon dioxide, there will also be small amounts of methane as well. As we know, both carbon dioxide and methane are greenhouse gases. So we've got the volcanoes constantly adding more greenhouse gases. We've got the oceans no longer capable of removing large quantities of CO2. We've got a reduction in the amount of photosynthetic life, which also is going to reduce the rate at which CO2 is removed from the atmosphere, and so that's obviously going to lead to an increase in greenhouse gas levels. This is going to increase the efficiency at which the Earth can retain heat, and so we're going to see a steady increase in global temperature. So this increase in global temperature is obviously going to cause the ice sheets to begin to retreat. And as the ice sheets retreat, what we're going to see is we're going to see the amount of the light coloured ice will obviously get smaller, whilst the amount of darker coloured ocean and continent is going to get larger. So this is going to mean a decrease in the Earth's bond albedo, so it's going to get darker in colour. Obviously, the darker an object is, the more heat it will absorb. So as the Earth gets darker, the planet is capable of absorbing and retaining more heat. And so this is also going to help to increase the Earth's global temperature. And so obviously, as the temperature keeps getting higher, more ice melts. That means the Earth's surface gets even darker, so even more energy is absorbed by the surface, and so on. So we have a reverse situation. We now have a runaway glacial retreat taking place. And eventually the process is going to return to essentially where we started. So that's essentially how the snowball Earth is envisaged to have occurred, and this is the mechanism which we believe stopped it. So this diagram kind of summarizes the basic process. So we have the ice caps either extending from the poles or some kind of continental landmass near the poles. The ice sheets will have extended to pretty much cover the entire surface of the Earth. As discussed, once we have this layer of ice, that's going to stop the oceans absorbing large quantities of CO2, and it's going to inhibit the ability of life to also strip CO2 from the atmosphere. So that means CO2 is going to increase in the Earth's atmosphere. At the same time, that CO2 is being pumped into the atmosphere by all this volcanic activity. That's then essentially going to lead to a strong greenhouse effect, which is going to cause the ice sheet to melt. So we're going to return essentially to our starting position. And eventually, this process may occur several times. So it's theorized that snowball Earth events could have occurred on several occasions and only stopped once the continents moved to higher latitudes. So once our continent shifted away from the equatorial band, obviously that's going to reduce the rate of erosion, and that means we're going to have a reduced rate at which carbon dioxide is stripped from the atmosphere as part of the weathering process. So essentially this is going to continue for several 100 million years until the continents start to move northwards and southwards away from the equator. So snowball Earth is an interesting model, but the data supporting it can be interpreted in several ways. So, after all, as we've discussed, it's difficult to accurately, relatively or numerically date material that doesn't have macrofossils or some kind of mineral that we can date, like zircon. So, these glacial deposits, although they appear to be similar in age, they may actually be of different ages. I mean, they may look like they're occurring at the same time, but there could be a difference in age of tens of millions of years. The other real problem is that a glacial event on this scale would have been devastating to the single-celled creatures that lived at the time. So essentially it could have induced a mass extinction. However, a mass extinction is obviously difficult to prove because the organisms we're dealing with are single-celled organisms, so that means no macrofossils, so we can't easily see any indications of a mass extinction, any indicators, of a mass extinction in the rock record for this time period. So the obvious question is okay, if snowball Earth's going to be terribly damaging to life on Earth, well, how did life manage to make it through this challenging period? So proponents of snowball Earth suggest that there are 3 possible locations where life could have survived the snowball Earth event or events. So these possible locations are around hydrothermal vents, within subglacial lakes, or in areas where the ice was thin enough to allow light to pass through and thereby allow photosynthesis. So the first environment, hydrothermal vents. So we've already covered hydrothermal vents in a previous lecture. So we know these are areas where hot water essentially is venting from the seafloor into the ocean. So obviously this hot water is going to help to keep that environment artificially warm, but also all the dissolved chemicals within that hydrothermal fluid are going to be a ready food source for single-celled organisms to survive. And so obviously once you have all these single-celled organisms, obviously then there will be animals that essentially eat them, and so on and so on and so on. So these hydrothermal environments offer a good reservoir for life to survive. Another possibility is that life could have survived in subglacial lakes. So a subglacial lake is where you have an ice sheet sitting directly over the top of a volcano. Now, as I'm sure you can probably guess, volcanoes by their nature are warm areas of crust. And so this means that the ice sheet is going to be heated up by the heat coming from the volcano, and so that's going to cause the bottom of the ice sheet to melt. And so this can lead to the formation of a subglacial lake, which is a body of water that's trapped between the ice sheet and the volcano surface. And obviously that body of water will be kept constantly warm by the heat from the volcano. And so this environment once again would offer a possible reservoir for life to have made it through the snowball Earth event. The final possibility is that life could have existed in the oceans in areas where the ice was relatively thin. So if the ice is thin enough, that will allow sunlight to pass through the ice into the water below, and obviously the single-celled photosynthesizing organisms that are in that water would still be able to photosynthesize and survive. So those three locations give us a possible way around the problems associated with snowball Earth. However, one problem does persist, and that problem is stromatolites. So the thing about stromatolites is they like shallow, warm seas. Now, we know stromatolites existed before snowball Earth, and we know stromatolites existed now. So if there was snowball Earth, if there was a snowball Earth event, clearly the stromatolites managed to survive. The problem is, of course, is that snowball Earth is going to get rid of large quantities of the ocean surface, and it's also going to cause global temperatures to drop substantially. So ocean temperatures are also going to decrease a lot. And so these would have been rather challenging conditions for stromatolites to survive. And so you have to kind of think of, well, how could stromatolites have actually made it through this situation? And the answer is, it's difficult to explain how they could have made it through. You would have expected them to have died out, but nope, they actually managed to make it through. So this has to be explained, and at the moment there isn't really a great explanation to explain how stromatolites managed to survive a snowball Earth event or events. So the jury is still out on snowball Earth. There is some evidence which would suggest that yes, there is the possibility of these large glacial events, but at the same time that evidence is a little bit difficult to date, and there are possible issues as to how life managed to make it through this massive global freezing event. So what about the Proterozoic atmosphere? So it's widely agreed that the Archean atmosphere contained no free oxygen, or at least extremely small amounts. So our present atmosphere contains lots of free oxygen. It's about 21% oxygen. So that means our atmosphere is considered oxidizing. Now, in the Archean, oxygen would have been created by two methods. The first is photochemical dissociation. So that's when an ultraviolet ray from the sun strikes a water molecule in the atmosphere, blowing that water molecule up. Obviously that releases the hydrogen and the oxygen. The other way that oxygen would have been produced during the Archean is obviously through photosynthesis. However, we've already touched on the fact that during the Archean there weren't many passive continental margins. So that meant that life would have had to have existed in more challenging, active continental marginal environments. And so this would have made it more difficult for life, so life wouldn't really have been as populous as it becomes in the Proterozoic. Obviously, as there's less photosynthesizing organisms, that would mean less oxygen produced. So when oxygen was produced by either photochemical dissociation or photosynthesis, it would very rapidly have been stripped from the atmosphere. So the oxygen would have been produced, and very, very soon afterwards it would have been removed in a chemical reaction. So this meant that the oxygen in the atmosphere couldn't build up because it was instantly being removed the second it was created. So the oxygen content of the Archean atmosphere would have been about 0.21%. So remember, the current level of oxygen in the atmosphere is 21%. So the amount of oxygen was extremely low. As we discussed, this level of oxygen couldn't really get any higher because the oxygen was being taken out almost as soon as it was created. Now, this is a process called buffering. Essentially, it helps to maintain equilibrium. So new oxygen can't build up because the second it's produced, it's also removed. So over the course of the Proterozoic, we see oxygen production through photosynthesis especially increasing. So at the end of the Neoproterozoic, that's the end of the Proterozoic, the atmosphere is modelled to have had anywhere between 2.1 and 7% oxygen. So once again, the current level is 21%. So it wasn't as high as it is now, but it was a significant increase compared to the Archean. Now, the amount of this oxygen obviously increases as you progress through the Proterozoic. So, obvious question, where did all the oxygen come from, and where did all the carbon dioxide in the atmosphere go? So, in the last lecture, we discussed cyanobacteria. So these are blue-green algae, and the structures that they can sometimes form called stromatolites. So, although these animals were present in the Archean, they didn't actually really start to appear widely until about 2.3 billion years ago. So that's the Paleoproterozoic, the early Proterozoic. So the reason for this is probably because in the Archean we didn't have many of the nice, boring, peaceful, passive continental margins. However, once we make it into the Proterozoic, we start to see the number of these passive continental margins increasing. This is a nice, safe environment for life to live in, and so life really begins to take off. So as these cyanobacterian numbers increase, both as stromatolites and as free-floating single-celled organisms on the surface of the water, the amount of oxygen produced by photosynthesis is going to start increasing dramatically. Now, on the other hand, obviously, if we're making oxygen through photosynthesis, we have to be taking carbon dioxide from the atmosphere. So as the amount of photosynthesizing organisms increases, we see a corresponding decrease in atmospheric carbon dioxide. On top of the amount of carbon dioxide being removed by the atmosphere, we also have to remember we do still have these reactions between the atmosphere and rocks, so we are going to also strip out some carbon dioxide when it reacts with calcium-bearing minerals to form carbonates, but most of the carbon dioxide is going to be removed by photosynthesis. So during the Proterozoic, there was more exposed crust, and so obviously this meant that there was more opportunity for for this reaction here to take place. So a reaction between atmospheric carbon dioxide and calcium-bearing minerals in rocks. So because there was all this exposed rock, yes, it means that this process would have also played an important part, but when it comes down to it, most of the change is due to photosynthesis. Okay, so this is a good place to stop part 1. So get up, have a walk around, get a glass of water, take 5 minutes, relax, and then please come back for part 2.